Chapter 5.3, the rational numbers. So in this chapter, we're going to go through basically what are fractions. So rational number is just kind of a fancy word for fraction, but there's a little bit more to it than that. There's a bit more of a definition than that. So we're going to get into that. We're going to get into working with fractions, as well as other representations of those fractions as the broader term rational numbers. Then we will go through different operations we can do with them, multiplication, division, addition, subtraction, and that will lead into our ability to work with fractions in problems, with rational numbers in word problems in later chapters. So first, what is a rational number? So the set of rational numbers denoted by Q, and so this is just like, remember the word set, right? We know what a set is now. Q is sort of like how we can write the integers, or the natural numbers, using a fancy sort of double-lined N, right? So that's the natural numbers. We use a fancy double-lined Q, which if I was writing it by hand, I wouldn't be quite as fancy as the typeface does, but that is our rational numbers. That's all that means, right? So we have the set of rational numbers is the set of all numbers that can be written in the form P over Q. That's sort of where that Q comes from, as we often use the letters P and Q when we're defining rational numbers, where P and Q are integers and Q does not equal 0. Now why does Q have to not be 0? Well, because if Q were 0, and Q being in the bottom of this, we'd be dividing, because it's P divided by 0, and that would be a problem, right? Because we're not allowed to divide by 0. It's like number 1 math rule, right? No dividing by 0, because it doesn't make any sense. So a key word here, and I'm going to keep bringing up this word, is the word can is important, okay? So first, some examples, right? We have numbers that are written in the form P over Q. Those are called fractions, right? So we have 1 over 3 and 3 over 4. Those are fractions. P is the numerator, Q is the denominator. So P being the one on top, Q being the one on the bottom, right? So in this case, P is 1, Q is 3. So numerator top, denominator bottom. Those are fractions. But not every rational number is going to be written that way. The point is that it can be written that way. So let's look at these other examples over here, right? So we can have negative numbers, so that's just a negative fraction, right? That's fine. But right here, this is not written in the form P over Q. This is not written in the form P over Q, right? So something's up with that. However, this one in the middle is called a mixed number, and we're going to talk a bit more about that later. But it is an equivalent form to a certain fraction, in this case to 5/3, and we'll get into how we figure that out a little bit later. But essentially, it can be written as P over Q, even if it isn't currently visually showing that. Similarly, the numbers 2 and 0 and any integer is rational because it can be written as a number over 1. So 2 over 1 and 0 over 1 are a way to write these numbers as fractions. So they can be written as P over Q. Thus, they are rational numbers. So basically, if you have a way to write it as a fraction, then it is a rational number. Things that are not rational numbers are called irrational numbers. That's the opposite. So all numbers that we kind of talk about can be split into these two categories, rational and irrational. And the numbers that you have heard of that are irrational would be like the number pi is an irrational number. There's no way to write that as just a simple number over number fraction. Or the square root of 2 is another one there isn't a nice square root of 2. So that number ends up being irrational. There's no way to write that as a nice fraction. So there are these numbers that are not rational numbers, but most of the easy numbers that we talk about, those are going to be rational numbers. Okay, so now let's talk about reducing fractions. So there are actually infinitely many ways to represent the same fraction, the same rational number. So for example, 1/2 is the same thing as 2/4, is the same thing as 3/6, is the same thing as 4/8, and so on. So let me just demonstrate that visually. So here we have, I'm going to call this a square. Let's pretend it's a perfect square. I'm splitting it into two parts. So this is 1/2 of the square, right? And this is the other half, so together they make a whole square. Okay, so I'm coloring in this half, right? Okay, now what if I split this into 4? 2 out of those 4 are colored in, but I didn't change what I colored. So 2 out of the 4 is still 1/2 of the square. If I draw a couple more lines here to make this, now there's 8 pieces. 4 of those 8 pieces are colored in. 4/8 is 1/2, right? That's all that means. Those are all equivalent. We can see that visually. It takes up the same amount of our whole. So a fraction is considered to be reduced when it is written in an equivalent form with lower, or we usually look for lowest, numerator and denominator numerals. Okay, so 1/2 is the most reduced we can be, but technically 2/4 is a reduction of 4/8. Just usually we're looking for the lowest terms. So to reduce a fraction, we divide the numerator and denominator by some common divisor. Okay? To get the lowest form, then we want to divide by what's called the GCD, or greatest common divisor. So in this case, if I want to reduce 54 over 90 to lowest terms, I need to figure out what is the GCD, greatest common divisor, of 54 and 90. So, how do I figure that out? Essentially, one way I like to do this, to be very thorough, is to make what's called a factor tree for each of them. So that's what I'm going to do up here. So I've got 54. I figure out what are two things that multiply to be 54. Okay, so I know 54 is 9 times 6. Okay, you can pick any pairing you know that multiplies to be 54. Then 9 is 3 times 3. And 6 is 3 times 2. And that's as far as I can go, because 3 and 2 are what's called prime numbers, and prime numbers just don't have anything that goes into them besides 1 in themselves, so I wouldn't be able to break this down any further except with 1s, right? Okay, so that's a factor tree for 54, and I'm just going to circle these bottom factors, okay? Then the factor tree for 90, what two things multiply to be 90? First thing I think of is 9 and 10, right? 9 times 10 is 90. And you can use a calculator if you need to help you figure this kind of thing out. Then 9 is 3 and 3, and 10 is 2 and 5. Okay, and that's as far as I can go. Those are all prime numbers. Okay, so now I just look for what is there in common between these two trees. And I don't just mean, oh, they both have a 9. No, that is something to be aware of. I want to look at the bottom factors. This is called the prime factorization. And I'm just going to look for matching stuff. So we've got, both of them have at least 2 3s. So we've got a 3 and a 3, right? So a 3 and a 3 on both of them. And both of them have a 2, right? Then nothing else is in common. The other 54 has a 3 in it, 90 has a 5 in it, so we're done. We've got all the commons. Multiply those together. Together that makes 18. 18 is their greatest common divisor. Now, if you didn't figure out, like if you didn't want to make the factor tree, you don't want to go through all that. If you happen to notice something they have in common, like maybe you just notice that 9 goes into both of them, you wouldn't necessarily have to start by reducing by that GCD. You could just divide 9 from both of them. So if I divide 9 from 54, I would get 6, right? So divided by 9 over 10. The problem is just this is not fully reduced. So how do I get it further? I look for what's a common factor between both of these. Well, 6 can be divided by 2, 10 can be divided by 2, so I can just go further. And when you look at that, 6 divided by 2 is 3, 10 divided by 2 is 5. Now both of those are well, they're actually prime numbers, but specifically they don't have any factors in common. And, well, 9 and 2 together, 9 times 2 is 18. So we really did end up dividing by 18 eventually. But if you happen to see that 18 was a GCD, you would just do that all at once, and you'd get 3/5. So you don't have to do all of this work that I just did. It's just this is one way to find that GCD if you're working with high numbers where, you don't really know where to start. Breaking them down, this is like just one way to find the best possible thing to divide by, so you only have to do that division one time. But 54 divided by 18 is 3, 90 divided by 18 is 5, so it's 3/5. Okay, so next, let's go on to, as promised, we're going to talk about mixed numbers. So mixed numbers versus what's called improper fractions. So in that first slide, I actually did show what an example of an improper fraction, but I didn't really talk about it. So there are two ways to represent numbers that are greater than 1 or less than -1. Mixed numbers and improper fractions. So a mixed number consists of an integer and a fraction. So 2 and 3/4 is read as 2 and 3/4, right? So it's whole number with a fraction next to it. This means 2 plus 3/4. Like technically there's this secret addition happening in the middle there. That's all it means. An improper fraction, on the other hand, is a fraction whose numerator is greater than its denominator. So our proper fractions have smaller numerators, like 1/2, right? But if I write 3/2, that is an improper fraction because it has a higher numerator. So 11/4 is an improper fraction that is actually equivalent to 2 and 3/4. Okay, but how do I figure that out? Let's talk about conversion. So our first type of conversion is converting mixed numbers to improper fractions. Okay, so to do this, we multiply the denominator by the whole number in front, and then add the product from step 1 to the numerator to get the new numerator. The denominator will remain the same. Okay, so that's a lot of words for a process that I promise is fairly simple. Essentially what we're doing is we are taking that 2 and making, or the 2 in this example, we're taking that 2 and making it into a fraction, but we want it to have the same denominator that the fraction that's next to it has. So we need to figure out how many fifths are in 2. And so we can actually figure this out visually first. So I've got two boxes, right? This is 1, 2, right? And I'm going to split it into fifths. 1, 2, right? That's split into fifths. Okay. So how many fifths total is this? This is 5/5. This is 5/5. And then we actually have 3 more fifths. So let's pretend these are approximately the same size as what I was drawing. The 3 more fifths, right? So our answer, we can see visually, is actually going to be 10 fifths plus 3 fifths for a total of 13 fifths. But let's see that algebraically, or arithmetically, really. So essentially we get 5 times 2, right? That's where I'm getting this 10 fifths, is because it's 2 groups of 5 fifths. So 5 times 2 is 10, plus 3 more, for a total of 13 fifths. Notice that that denominator never got touched. We are counting a number of fifths here. And maybe, depending on what this numerator becomes, we might reduce it afterward if we got a certain number up there. But in general, that's not usually what's going to happen when you're converting from mixed numbers unless the mixed number itself wasn't reduced. Okay, now let's try this again with 4 and 7/8. So arithmetically, our process is going to be, we take the 4 and we multiply by 8 to get how many eighths total are in 4 whole numbers, 4 wholes, right? So that'll be 4 times 8 is 32, and then we add that 7. So 32 plus 7 is 39 eighths. But again, let's just visualize this just to really solidify our understanding what's happening here. So make 4 boxes. There we go. And then I'm going to split them into eighths. So this, like that. So that's split into eighths, like this. There we go. Eighths. Okay. Right? So that is 8 eighths. And then 8 more eighths, 8 more eighths, 8 more eighths, for a total of 32 eighths, right? If I counted each of these triangles, I'd have 32. But then we need that 7 eighths. So I make my box, but I'm not going to actually finish it. It's more like this. This is going to look a little awkward, but something sort of like this. It's not the best drawing of it, but there's 7 eighths there. So there's 7 eighths. And now if I counted each of these triangles, I would have a total of 39 eighths. So you can always work with your fractions visually if that helps you to understand what you're doing. Don't forget what these fractions really represent. There's always a visual representation of what's going on, and you want to remember that so you don't get bogged down in thinking that these numbers don't mean anything in the real world, right? Okay, now let's do the opposite, where we're going to take an improper fraction and convert it into a mixed number. So, to do this, we will divide the numerator by the denominator, isolate the quotient and remainder, and then the quotient is the whole number part of that mixed number. The remainder will be the new numerator. The denominator will, as before, remain the same. Okay, again, it's a lot of words for something that is not too many steps. However, this is going to involve having to do some division. So that division is coming back, remember, but at least it's in base 10 again. So much simpler division than we were working with back in chapter 4, right? So we're going to start with one that's not too bad. We've got 8 fifths. And again, we can visualize this, 8 fifths. So I'm going to draw this one out just for demonstration purposes. But I'm not going to want to draw 225 eighths, right? So I'm only going to visualize this first one. So 8 fifths, I take 5, I've got 5 fifths, and then I actually have, like, if I split this into 5, I'm coloring in this whole thing. I'll just visualize this by coloring them this time. And then 3 more, right, until I get 5 fifths, and then 3 more fifths here, right? Because I kind of ignore the ones that are over here. These don't matter. So that's a total of 8 fifths. So we can see this is 1 and 3 fifths. That's what the answer we're aiming for is. So let's see how we would get that using arithmetic. So I take 8 and I divide by 5. 8 divided by 5 is 1, right? And I subtract off 5. Right, and we're doing long division here, so I subtract that 5, I'm going to get 3. 3 is my remainder. So I get 1 and 3 fifths, right? So this number becomes the whole number. This number becomes the numerator of the fraction part. Okay, so now let's apply that to a much larger one that we can't as easily visualize. Technically, you could draw this out, but it would take a while, right? So we're going to take 225 and divide that by 8. So how many 8s go into 22, right, into 22? So we got 8 times 2 is 16, right? That's as close as we can get. So put a 2 up top, subtract off 16. That's going to be 6, and I'll bring down my 5 to get 65, so I'm not done yet, right? So I'm going to ask again, how many 8s go into 65? Well, 8 times 8 is 64. Right, so I got 28 up top, I subtract off 64, and I have 1 left over. And so that tells me I've got, just like before, right, this is going to be my whole number, this is going to be my numerator of my fraction, and then my denominator stays the same. So I get 28 and 1/8. Alright, so that's a couple ways we can represent fractions, but those aren't the only ways, or a couple ways we can represent rational numbers specifically, but those aren't the only ways. We can also represent a rational number as a decimal. And so every number can be represented as a decimal in some way. However, one specific thing to understand about rational numbers is their decimal forms are either repeating or terminating. Okay? If they aren't repeating or terminating, you don't have a rational number. So, for example, once again, pi, 3.141592, all of that, never repeats itself, and it never stops. That's what terminating means. It stops at some point. Pi doesn't. So pi never repeats or terminates, means it's an irrational number. But, for example, decimals that do stop would be 1/2 is 0.5, 3/4 is 0.75, 4 and 13/20 is 4.65. Those decimals stopped. They stopped pretty early. It doesn't have to be the case. It could stop, 100 digits down the line, and that would be fine as long as it stops at some point. Repeating decimals, on the other hand, are decimals that repeat some sequence of digits infinitely. Like, not just 1.2323 and then a bunch of mishmash changes, no repetition. It has to be that the repetition happens infinitely on and on forever. So 1/3 is 0.33333 repeating infinitely. And we actually represent this repetition by just drawing a little line over top of what is being repeated. So instead of having to attempt to write infinitely many threes, I would write 0.3 with a line over it. And that means the 3 is getting repeated on and on and on infinitely. 23/99 is 0.2323232323, and so on and so on and so on. Okay? So we write this as 0.23 with the line over it to denote that it repeats, right? 8 1/6 is 8.166 and on. But only the 6 is getting repeated here. So I only put the line over the 6. I write 8.16 with a line over the 6. Okay? So writing this in this way allows it to look like it's a terminating decimal, right? Because we stopped writing it at some point, but we have made a point of saying all of what it is. Like, we're not ignoring any of the digits the way in pi we do ignore a lot of the digits. When I just say pi is about 3.14, I'm ignoring everything else. But if it were 3.14 repeating, and I put a line over it, then I'm not ignoring everything. I'm acknowledging that it's there. But that's not what pi is. I can't do that with pi. Alright, so here we are going to find the decimal equivalent of the following fractions. And so what's nice about finding decimal equivalents is we just have calculators on us to do this. So you'll be allowed to use a calculator to find these. This is just a little bit of practice. So I'm going to kind of quickly go through this. But all you have to do for non-mixed numbers, so looking at A, B, and D, non-mixed numbers, all you do is you just plug this in to your calculator exactly as it says. 4 divided by 5. Make sure you're doing it in the right order. The divided by comes after the numerator, right? Numerator divided by denominator. 4 divided by 5 is 0.8. 21 divided by 25 is 0.84, but this is negative, so put a negative there. 14 divided by 99. That one's going to appear a little different. It's going to be 0.1414141414, and so on. And your calculator will stop probably 10 digits down the road or something like that. So we will write it with that repeating line over the 1, 4. 1 and 536 has like a little extra to it. We can still just type in 5 divided by 36 to get 0.13, and then the 8 is going to be repeating. But we just have to remember there should be a 1 out front. That is not 0.138 repeating. It's 1.138 repeating, right? Because we only really need our calculator to tell us what the decimal part of this is, but the whole number is right there. It's the 1. Okay, but converting decimals to fractions is a little bit trickier. So, behind me you'll see I have noted the position names of some of parts of a decimal, right? So we've got the units position is where the whole number like goes, right? We kind of are familiar with the ones place is essentially what it is, right? Then we've got the tenths, the hundredths, the thousandths, the 10,000s, the can't really see it, but it's the 100,000s, the millionths. Again, the THs denote that we're, on the right side of the decimal. But it's same place value stuff that we've talked about before. Now, given a terminating or repeating decimal, we can convert to a fraction using the following method. So for terminating, we take note of the position name of the last digit of the decimal, and we place all digits after the decimal over that power of 10, right? So 0.285714. Let's look, right? 285714 is the example that's up here. This is, again, I'm sorry, I'm in front of it, but it is the millionths position. So we are going to write that as 285714 over 1 million. That's it. That's the fraction. Now, is that reduced? No, it is not. This can be reduced from there, but at least we have a fraction to start from. After that, we go find our common divisors, etc., to reduce it. For a repeating one, it's a little bit trickier. There's like a whole process, okay? So bear with me here. It does take a little bit of extra sort of algebra. So here I have 12.142 repeating. Okay, so what am I going to do? I am going to basically notice the whole process, right? I'm just writing it all out at once. So I'm going to say, let's call n my number, this 12.142 repeating, okay? 100 times my number. Okay, but why did I pick 100? I just picked that to go up to move this decimal. Essentially, when I multiply by 100, I move my decimal over 2 times. If this had been 1.214 and then the 2 was repeating, I would multiply by 1,000 to get it to move the decimal to move over 3 times. Basically, I multiply by a power of 10 that will move my decimal so that it's right in front of the repeating part. Okay? So 100 times this number. So 100 times this number is 1,214 point the 2 repeating. Okay. I also am then going to go up one more level. So 1,000 times this number is 12,142.2 repeating. Now notice, that's because this is technically 0.2222, like that's all it is, so it's just shifting it over a little bit, so there is that too, but this is what's getting repeated, okay? So, oops, not trying to get out of here. Now, what we're going to do is we're going to take this number minus this number, right? So it's 1,000n minus 100n, right? This minus this. You can use a calculator to do this, right? 1,000n minus 100n is 900n. That is a little bit of algebra, but that's about as much as we're going to get. Then, when I do that subtraction, I actually subtract off these repeating 2's, right? Because they're the same thing, so they kind of just cancel out when I do that subtraction. And that's what we're going for. So when I do that subtraction, I get 10,928 is equal to 900n. Now I have to solve for n. So again, it's a little bit of algebra. Solving for n, we divide both sides by the 900. Like so. And that's 10,928 over 900, which does reduce again to 2,732 over 225. But our main idea is to try to at least get it into fractional form. The reduction is just a little bit extra if you're asked to give it in lowest terms. So yes, this process is a little tricky. It is algebraic, a little bit more than we tend to do in this class, but this is about as tricky as anything. Like, this is probably the hardest thing to do in this particular chapter, is that process. So it's going to be a similar process every time, but you do have to know which power of 10 you're multiplying by to move that decimal, but it's always just going to be powers of 10, 100, 1,000, a million, whatever. That's all it's going to be. So you're not working with any particularly difficult numbers aside from the original decimal, right? So the multiplication part isn't too bad. All right, speaking of multiplication, let's talk about multiplying fractions. So to multiply two fractions, we multiply the numerators, then multiply the denominators separately, top, bottom. So a over b times c over d will equal a times c over b times d. Okay? So 2 over 7 times 5 over 8 will equal 2 times 5 over 7 times 8, right? So that's 10 56ths. But we do want to give our answers in lowest terms whenever possible. So I'm going to reduce this. What is in common between 10 and 56? Well, both of them can be divided by 2, and that's the best I can do. So dividing both of them by 2 will give me 5/28, and that's as far as I can go. Next, I've got negative 2/3 times negative 4/9. Those negatives get multiplied together on the top. So negative times a negative is actually a positive number. So negative 2 times negative 4 is positive 8 over 3 times 9 is 27. That can't be reduced. But I want to make a note here that had this been written as negative 2/3 times negative 4/9, for example, we use parentheses here. Please don't write this. This is not good form because it looks like times minus. What is the operation here? Is it multiplication or is it subtraction? Like, this isn't good form. You want to write parentheses to preserve that is a negative sign, not a minus sign, even though it kind of gets you to a similar place when for what you would think it means. Mathematically speaking, it's not the same thing. So, if it's negative 2/3 times negative 4/9, it equals the same thing. If the negative is out front, or the negative is on the top, or the negative is on the bottom, it doesn't matter, it equals the same thing. Because just negative 2/3 is the same thing as negative 2 over 3, which is the same thing as 2 over negative 3. All of those mean the same thing. As long as there's one negative there, it all means the same thing. Okay, so what about mixed numbers? So here I have 1 7/8 times 2 1/4. I'm going to tell you, technically speaking, you could multiply them as mixed numbers, but you're going to have to do a lot more work to do that because, remember, the mixed number is like addition here. 1 plus 7/8 times 2 plus 1/4. If you're going to multiply that way, you're going to end up with 4 terms because 1 has to be multiplied by 2 and by 1/4. The 2 has to be multiplied by 7/8 and by the 7/8 has to be multiplied by the 2 and the 1/4. So you end up doing this distribution, and it's a lot more complicated than we want it to be. So instead, we're just going to make them improper fractions, right? Because we learned how to do that. So we're going to make these both into improper fractions. 1 7/8, well, 1 is 8/8, so 8 plus 7, 15/8. 2 1/4 would be 8 fourths plus 1/4 is 9/4. So here we have the improper fractions, right? These are the same. These are equivalent forms. Now I multiply those together in the same way I multiplied everything else. That's nice, right? 15 times 9 is 135. 8 times 4 is 32. And again, we want to simplify this, but in fact, I'm actually going to rewrite this as a mixed number because I want to stay in the form that I was given. Is that necessary? No, not necessarily, but I'm going to do it anyway. So let's get a little practice. How many 32s go into 135? Right, so we do that division, 135. I'll tell you it's actually, I believe, 4 32s go into 135. So this will be like that. Subtract that off, and we will end up with 7, I think. So this is 4 7/32. So we can convert it back. We could also reduce maybe, but in this case there actually isn't any reduction that can be done. So I'm just writing it as a mixed number to make it look nice. Because in some cases, mixed numbers do look nice. In higher level math, we prefer improper fractions, but in like real world situations, mixed numbers tend to be the preferred way of presenting that type of number. All right, before we get on to division of fractions, we need to learn one more definition. So that is the reciprocal. The reciprocal of a number is 1 divided by that number. The product of a number and its reciprocal will always equal 1, and all rational numbers except 0 have a reciprocal. Essentially, a reciprocal is just taking a fraction and flipping it upside down. Like, that's really what it does. That's what 1 divided by a number does, is it just flips it upside down. Okay? So 3 1/3. Now, flipping it upside down, I mean in the sense that 3 can be written as 3 over 1. So flipping it is 1 over 3. And if I do 3 times 1/3, I get 3 over 3, which is 1. 3/5, 5/3. -6, -1/6. It keeps its sign. So if it's positive, its reciprocal is positive. If it's negative, its reciprocal is negative. Because negative times negative equals a positive. So if I want to multiply -6, -1/6, I get positive 1 like I wanted. The reason this is important is because when we divide fractions, we basically just take the second fraction, the one that's being divided by, and multiply by its reciprocal. Okay? So a over b divided by c over d, the c over d gets flipped over for multiplication. So we do a over b times d over c, and we do the same multiplication we did before, where the ad is in the numerator and bc goes in the denominator. So 1/6 divided by 3/5 is actually the same as saying 1/6 times 5/3, because 5/3 is the reciprocal of 3/5. Notice that the 1/6 didn't change, only the 5/3 changed. When we multiply these together, I get 1 times 5 over 6 times 3, which is 5/18, and there's nothing we can do to simplify that. -2/9 divided by 3/13. Once again, we're going to flip over that 3/13. We're also going to remember what I said about negatives. I'm going to bring that negative into my fraction by just putting it on top of the ninths, like putting it with the 2, just so it's a little bit easier to read. So I'm rewriting this as -2/9 because these are exactly the same thing. And then I'm flipping over my 3/13 to get 13/3. Now I do my multiplication, -2 times 13 over 9 times 3, which is -26/27, and once again, that does not simplify. Alright, so the last operations we're going to talk about are addition and subtraction, which are actually a little bit trickier than multiplication and division. If you have a common denominator, which means the denominators are the same, then they're not hard at all. However, if you don't have a common denominator, we have to do a little extra work, okay? So in this case, if you have a common denominator, where the denominators are the same between the fractions that you're adding or subtracting, we just work with the numerators, essentially. So a over b plus c over b is a plus c over b. Notice that the denominator remained the same the whole time. We do not add the denominators, do not change the denominators at all. Similarly for subtraction, a over b minus c over b is equal to a minus c over b. So visually, let's look at this. 1/8 plus 3/8. So that is going to be, I'm just going to draw a box, right? I'm going to split it into 8 once again. Okay, so there's my 8 triangles. Cool. Each of these is 1/8. And so I've got my 1/8 right here. When I add, I just mean I want to gain 3 more of these triangles. Plus means just gain 3, right? So 1, 2, 3, total of 4/8, right? So that's 4/8 total. Okay, which hopefully we remember from before, 4/8 is in fact 1/2. But that's just 1 plus 3 over 8. 4/8, which does simplify to 1/2. But the point is before reducing, I kept my denominator the same because visually speaking, I'm still working in eighths. It didn't change what portions of the square I was working with. I was working with eighths the whole time. I just gained more eighths. So that portion of the square did not change. Just the number of those portions changed. So I got 4 of them now. Okay. So 19/24 minus 5/24. I'm not going to draw the square here, but think about it. I take the square, I divide it into 24 pieces. I have 19 of them colored in. Subtracting means I'm uncoloring 5 of them. Part of why I'm not doing this is because it's hard to erase here. But 19/24 minus 5/24 is just 19 remove 5 of those 24ths. 19 minus 5 is 14, so it's 14/24 will be left, which does simplify because both 14 and 24 are even numbers. So we can divide both of them by 2 to get 7/12, and then there's nothing more in common between them. That's as reduced as we can get. Now, if you're working with unlike denominators, it gets a little bit trickier. So to add or subtract 2 fractions with different denominators, we rewrite them in equivalent forms that do have the same denominator. Now, sometimes we only have to change one of the fractions, but oftentimes we end up having to change both. So we can find an equivalent fraction simply by multiplying the numerator and denominator of that fraction by the same number. In the same way that before we were reducing by dividing the top and bottom by the same number, now we are unreducing, expanding, I guess. So we multiply numerator and denominator by the same number. Multiply, do not add numbers here. We're multiplying the numerator and denominator. That's how we get our equivalent forms. So 4/7 and 1/6. We need a way to relate 7ths and 6ths. Okay, so we need them to have the same denominator. Basically, how do we figure out what that denominator is going to be? The easiest thing we can do is multiply by each other, essentially. So if I get 7 times 6 and 6 times 7, they're going to be the same number, right? So in part B, we'll see another way to do this, but in this case, there's nothing in common between, there's no common divisor between these, so what's called least common multiple, which means a multiple is things that you can multiply to get to. The least common one is whichever one that both 7 and 6 share. It's going to be 7 times 6, which is 42. So I'm going to get these denominators to be 42. To do that, I multiply 4/7 by 6/6, and I multiply 1/6 by 7/7. Notice that in doing this, what am I actually multiplying by? I'm multiplying by the number 1. 6/6 is 1. That's what that is. That's why I'm allowed to do this. It's because multiplying by 1 doesn't actually change anything. It doesn't change the meaning of my number. So that's why I'm allowed to do this. It's why it doesn't change it's an equivalent form. It just looks a little different, but I really just multiplied by 1, right? And anything times 1 doesn't really change. So, just remember, you have to multiply top and bottom both by this number or else it doesn't work. Okay, so 4 times 6 is 24, and 1 times 7 is 7, so we get 24 40-seconds plus 7 40-seconds. Shared denominator, so now we can just add like normal to get 31 40-seconds. And again, we keep that denominator 42 now. Okay, now for my 12ths and my 30ths, I could multiply 5/12 by 30/30 and 11/30 by 12/12. You can always essentially do that, where you multiply by each other. That will always get you an equivalent form, but for a lot of numbers, this will end up giving you one that needs to be reduced a lot more. In this case, yes, this one would need to be reduced if I did this. So instead, I'm going to find a lower number that is equivalent. And so I can do this again by bringing out my factor trees, or maybe you just happen to know some multiple of 30 and some multiple of 12 that are the same, right? I'm going to do this by factor trees real quick. So I'm going to write out my factor tree for 12, and then my factor tree for 30, like so. Okay. And I'm going to see what they have in common. So we've got basically the best number I can get. I'm going to, for a least common multiple. So this is the technique to find the least common multiple. Their greatest common divisor is 2 times 3. Right? The 2 and the 3. Because they have those in common. So their least common divisor is 6. But that doesn't really matter. That's not what we're looking for here. We're looking for their least common multiple. So it's a little bit of a different process. So essentially, I cross out, I got 12, this is 12, and then I'm going to make 30, like this. This right there is 30. So I've basically accounted for all of those numbers in the factor tree by doing this. Do you have to do it this way? Absolutely not. If this makes no sense to you, don't do it this way. Just multiply by 30 over 30 and 12 over 12 if you have to, and then reduce. That's fine. Alternatively, you could just sort of think out what are all the multiples of 12? I could go 12, 24, 36, what's after 30? 48. Like, I could do that, and then 30. Oh, what's the next one? 48, 60. Yeah, there we go. Then 30 and 60. So, in fact, I got there. That's their least common multiple, which happens to be this. So, there are different ways you can do it, right? You want to find the way that makes the most sense to you. So, we've figured out that their least common multiple is 60. So, what I'm going to do is I'm going to take 5/12 times 5 over 5, because 12 times 5 equals 60. And 11 30ths times 2 over 2, because 30 times 2 equals 60. So I'm going to get those 60ths in the denominator. So whatever method you need to use to get that 60 is your least common denominator, use that method. There's plenty other ways to do this. This is just one that I know how to do. And if the factor trees don't make sense to you, don't use them. Alright, so when I do this multiplication, I end up with 25 60ths minus 22 60ths. And now I'm just going to do subtraction, right? So 25 minus 22 is 3. And in this case, I actually do end up having to reduce again. That's not always going to be the case, but once in a while you do end up with a reduction after the subtraction, even if I use my least common denominator. So 3 60ths can be reduced if I divide 3 by 3, 60 divided by 3 to get 1/20th, which is a completely different denominator. It wasn't even related to the other things.